Okay, so we are going to continue reviewing. My last survey of calc class, we covered problems, not all of the problems, but we got up to problem 40. And so now I'm going to continue here. And then I'll post all the videos from all sections, and it should cover the entire review for the test coming up next week. If you're in group 1, make sure that you email me and let me know which day you want to take it, Monday, Wednesday, or Friday. It's first come, first serve, so I'll get you signed up in there as quickly as possible so that you can get your slot that you want. But I may have to put you somewhere else, not sure. So we want to find the specified area, and that's the area under the graph of f over the interval from -3 to 3. So you can see here, this is a function defined piecewise. So it has this function 4 minus x squared for negative values of x, and it's equal to 4 for positive values. So I needed to divide up my integral. So from -3 to 0, I'm going to calculate the integral from -3 to 0 of 4 minus x squared dx. And then I'm going to add to that when x is greater than or equal to 0. So that would be from 0 to 3. And the function this time is going to be 4 dx. So this will give me the area under the curve. And doing the integration, I get 4x minus x cubed over 3. And then I'm going to evaluate it from -3 to 0. And then I've got 4x evaluated from 0 to 3. So you're going to plug in the top number. And you always plug in the top number and subtract what you get when you plug in the bottom number. So it's going to become 4 times 0 minus 0 cubed over 3. And then you're going to subtract from that what you get when you plug in -3. And then we're doing the same thing for this part. We're adding 4 times 3 minus 4 times 0. So this, of course, is 0 here. And this is 0. So really, I'm just doing this calculation here. I have -12 plus, because of the double negative here, 27 over 3, which is 9. So -12 plus 9 is going to be -3, but then I'm subtracting -3. So I'm subtracting a -3. And then I'm adding 12, 4 times 3. So that's going to be 3 plus 12, and that's 15. Okay. Now, number 41 is an interesting problem. Let's take a look at number 41 now. This is from review 4. I'm going to write down your name for attending, Allison. So, and let's see, is anybody in Zoom? Not yet. Okay. All right. No. Well, what happened was, the reason why I think no one is in Zoom is because I didn't have a link set up. Somehow it ended prematurely. So I quickly set up a link, but I think a lot of people come in, check in, and it's not there, and they think, oh, we don't have class. So it was my fault. But anyway, so we're integrating this time from -3 to 9. This is number 41 on the review. And it doesn't look like it, but this is actually a function that should be defined piecewise, at least for integration purposes. It's the absolute value function. And if you think about it, here's the absolute value function in the Cartesian plane. And when x is less than 0, this is y equals -x, this line right here. And when x is greater than 0, it's y equal x. So we have two pieces put together to get the absolute value function. So our function the absolute value of x is going to be defined piecewise. So it's going to be x if x is greater than or equal to 0, and it's going to be minus x if x is less than 0. And it looks like somebody's coming in now, so let me fix that screen there. Okay. All right, so we're going to integrate them separately, and so we're going to go from -3 to 0. We're going to use this, I'm sorry, this one right here. So it's going to be from -3 to 0. It'll be -x dx. And then from when we get on for the positive numbers, it's going to be from 0 to 9. So we're going to go from 0 to 9 of x dx. And so the integration, I've got you as attending, Frank. Let me write your name down. I don't have an assignment out there, so I just wrote your name. Okay, so we have here taking the integral, we get -x²/2, and we're evaluating that from -3 to 0, and then we're adding to that x²/2 evaluated from 0 to 9. And so we plug in the top number first, so it becomes -0² minus -3² plus 9² minus 0² Okay, so that gives us plus a positive 9/2. And then we're adding to that 81/2. So that's going to be 90/2, which is 45. Okay, so the interpretation is if you go to -3 and then 2, 3, 4, 5, 6, 7, 8, 9. It's that shaded area under the graph there is 45. Okay. So that's number 41. And moving on, I'm going quickly through this because I'm going to post these videos and I want to be able to cover everything. So number 42 on the review. We have a function. It says find the area of the shaded region. And it gives us a picture here. Okay, so we have a function f of x, and then g of x equal to 0. Well, that's just the x-axis. So you want to find the area bounded by those two curves, and the x-axis is one function, and the other function is your f, which is this curve right here. So when you're finding the area between two curves, the way you set up the integral is you integrate when you have you take your top function and you subtract your bottom function, and then you integrate here on the x-axis. It's going to be 0. That's this function right here is 0 minus this function. That's your f. And it's going to go from -5 to 0. And then you're going to add to that the top function, which is f of x minus g of x from 0 to 4. So let me write that down so you can see that. So we're integrating from -5 to 0, and this time it's going to be g of x minus f of x. And the top function always comes first. Then you're going to add to that. Notice they switch. Now f is on top, so we're going to go from 0 to 4, and we're going to have f of x minus g of x. If you just integrate from -5 to 4 and you don't separate it, what it's going to do is it's going to take this area and subtract this area. And so your number is not going to represent the total area. You want the total area. And when you're finding the area between two curves, in this case, it's the x-axis, then we just take 0, 0 minus f, and then f minus 0. We separate them when we integrate like that so that we get the positive value for both regions. Okay, so now let me just put that in. This is going to become the integral from -5 to 0 of minus f of x, because this is 0, right? G of x is 0. And f of x is minus x cubed minus x squared plus 20x. G of x is equal to 0. So we have 0 minus negative x cubed minus x squared plus 20x. And then we're adding to that the integral from 0 to 4 of just plain old f of x minus 0, which is just f of x. So minus x cubed minus x squared plus 20x. And then you want to distribute this negative. So you distribute it here, here, and here. And so this is going to be positive, positive, and negative like that. So you're going to get the integral from -5 to 0 of x cubed plus x squared minus 20x plus the integral from 0 to 4 of, and I forgot my dx. You always got to put your dx there. Okay, now we can do the integration. This is going to become, remember, you add 1 to the exponents of x to the 4th over 4 plus x cubed over 3 minus 20x squared over 2, evaluating from -5 to 0, plus minus x cubed over 3 minus x squared over 2 plus 20x squared over 2, evaluated from 0 to 4. And so simplifying, I did this wrong here. What did I do? I should have added 1 to the exponent. I did it here, but I forgot to do it there. Sorry about that. That should be a 4 and a 3. There we go. That's better. You always, when you're integrating, you always add 1 to the exponent and divide out by your new exponent, just like I did over here, but I somehow messed it up there. Okay, so now we plug in the top number, and that's going to be 0, 0, 0. And then we subtract what we get. So it's going to be -5 to the 4th power over 4. And then you're going to plug in -5 cubed over 3. Now, -20 divided by 2 is just -10. So it's going to be -10 times -5 squared. And we have 0. That was when we plugged in 0, we got 0 minus this. Then you're going to have plus, you're going to plug in the 4 minus 4 to the power of 4. Now be really careful here with details like this. Here I'm plugging in -5 and raising it to the 4. So the negative gets raised to the 4 and therefore becomes positive. Whereas here I'm plugging a 4 in, raising it to the 4th, and so the negative is on the outside. So those are some details that you want to be careful about. That's, of course, 10 times 4 squared. And then you're subtracting from that 0, because when I plug in 0, it's all zeros. So doing that on your calculator, and I'm not going to take the time because we've got a lot to get through today. So I'm just going to give you the answer because I happen to have it here. You get, let's see, 2521 over 12. Of course, you'll have your calculator to do that. I'm going to try to keep the test super simple. So I probably wouldn't put one like this. It's just a little too messy. So for the next one, in order to save time, I'm going to set it up for you, and then you can do it on your calculator. So here, 43 is a similar problem. We have the area between the curves. And remember, you always take the top function minus the bottom function. And so you're going to have two separate integrals. And that's because on the left side here, the top function is your f and the bottom function is your g, whereas it's the reverse over on this side. So you have to have two separate integrals. So this is number 43. You have f of x equals x cubed plus x squared minus 6x, and then the g of x now, instead of 0 this time, it's 6x. Okay, you're finding the area between these two curves. So you're going to integrate, looking at the picture here, you're going to integrate from -4, that's this point, the x value is -4, to the origin, so your x value is 0. So it's going to go from -4 to 0. And this time your f is on top, so it's going to come first. You're going to have x cubed plus x squared minus 6x. And then you're going to subtract the g of x, which is 6x. Okay, so this is f of x minus g of x. That's what this whole thing is right there. And then don't forget your dx. We haven't integrated yet. So that would be the area on the left here. Now to get the area on the right, you're going to go from 0, because the x value at 0 at the origin is 0. And then the x value of this one here is 3. So you're going to integrate from 0 to 3. And this time you're going to have g of x minus f of x. So it's going to be 6x minus your f of x, which is right here. And you got to subtract the whole thing. So you've got the integral from -4 to 0 of x cubed plus x squared minus 12x dx plus the integral from 0 to 3 of -x cubed minus x squared. I'm just distributing the negative. This is going to be 6x plus, because of the double negative there, plus 6x. That's going to be plus 12x dx. So when I do the integration, I'm going to get x cubed over 3 plus, oh wait, that's a 3 there. I copied that wrong. So x to the 4th over 4 plus x cubed over 3 minus, it's going to be 12x squared divided by 2. So that's going to be minus 6x squared. That's the antiderivative evaluated from -4 to 0 plus, and then it's going to be minus x to the 4th over 4 minus x cubed over 3 plus 6x squared evaluated from 0 to 3. And I'm going to do one more step. When you plug in 0 at the top, it's going to be 0. So you get 0 minus whatever you get when you plug in the -4. So that's going to be -4 to the 4th power over 4 plus -4 cubed over 3 minus 6 times -4. Make sure you keep track of your signs. This is going to be positive because you've got negative to the 4th is a positive. This one's going to be negative. Negative cubed is negative, and this is double negatives, positives. Then you're going to add to that what you get when you plug in 3. So that's minus 3 to the 4th. Now, this is minus 3, but the negative is not raised to the 4th because I'm plugging in 3. I'm not plugging in -3. I'm plugging in 3. So that negative stays. It's on the outside. And you just have -3 to the 4th, as opposed to this where the negative is inside the parentheses. And you know what I'm saying. So here we have and then you subtract off 0 because when you plug in 0, you get 0. I'll let you figure that out. The answer is, and you're going to do that on your calculator, is 937 over 12. Okay. Again, I'm going to try to keep the ones on the test simple so you don't have too much work like that to do. Okay, another thing you're going to be able to do from section 3.7 is find the elasticity of a function, of a demand function. So here we're given so you've got Q, this is number 45 on the review. Q equals your demand function, which is 300 minus 4x. And I'm going to give you the formula for elasticity. It's E of x equals minus x times the derivative of the demand function divided by the demand function. That's your formula for elasticity. I'll give that to you. So when it says find the elasticity, you're just going to take the derivative. So d prime of x is -4 because this is a linear function and the slope is -4. And you're just going to plug that in along with your original function into the formula. And so you get E of x is equal to minus x times -4 over 300 minus 4x. And so that's going to be 4x over 300 minus 4x. That's your elasticity. Okay. So know how to find elasticity. And let's see. You also need to be able to interpret what the meaning is when you're given an equilibrium point. So for the demand function given, find the elasticity at the given price and state whether the demand is elastic, inelastic, or whether it has unit elasticity. So this is problem 50 on your review. And so you should be able to do a problem like this. So you're given a demand function, 600 minus x. And you're given a price, x equals 65. All right. And you want to find the elasticity. For that price. So it's the same as what you would do in the last problem. This time, you're just plugging in a number at the end. So again, the elasticity is minus x times the derivative of your demand function. The derivative of the demand function is -1, right? It's linear, so it's just the slope. So you get negative x times -1 over 600 minus x. And so you got x over 600 minus x. And so you're going to get, when you plug in the 65, you get 65 over 600 minus 65, which is going to be 65 over 535. And you can simplify that by dividing out by 5. So it's going to be 13 divided by 107. Now, you need to know this for the test, okay? If it's elastic, then your elasticity is greater than 1. So if E is greater than 1, then it's elastic. If E is less than 1, then it's inelastic. And then if it's equal to 1, it has unit elasticity. Okay. Now, also, when you want to find when you want to maximize revenue, you set E equal to 1. So that's important. And we'll do a problem like that. To maximize revenue, set E equal to 1. Solve for X to find the price. Okay, make sure you know that, because there's a problem that'll say, how do you get the maximum revenue? And then you're going to know, oh, I set E equal to 1 and solve for X. Okay, so make sure you know that. Now let me do a problem like that. So anyway, in this problem, before I move on though, you can see that since the numerator is smaller than the denominator, this number here is less than 1. And so it's inelastic. Okay. Let's see if I got that. Okay. So I want to do some more where I'm showing you how to calculate the elasticity, because some of the functions are a little more complicated. The two examples that I did here were linear. And so I probably should do one that's not quite so. Okay, let's do another one. All right, I'm looking at number 52. And you're given Q is equal to D of X, which is the square root of 750 minus X, and X equals 590. Okay, so you're going to first find the derivative. But before I do that, I want to, whenever you have a radical like this, you want to write it as a power. Okay, so when I take the derivative, I bring 1/2 times 750 minus X, and then I subtract 1 from the exponent, so that's going to become negative 1/2. And then by the chain rule, I have to multiply by the derivative of what's inside. The derivative of 750 minus X is negative 1. So this is going to be 1/2. And then this negative means it's going to go in the denominator, and I'm going to take the square root. So, and the negative 1 can be multiplied by the 1/2. So this whole thing is going to be times the square root of 750 minus X. Again, the square root comes from this 1/2, and the fact that I put it in the denominator comes from this negative exponent. And this negative is multiplied, so I can just put it in front of the 1/2. So just to write that a little nicer, it's 1 over, or negative 1 over 2 square root of 750 minus X. This is the derivative of the demand function. So now I can calculate the elasticity function, or find the elasticity function, and that's minus X. Again, I'm going to give you this formula, minus 1 over 2 times the square root of 750 minus X divided by your demand function, which is the square root of 750 minus X. And to simplify that, it's going to be minus X and then times negative 1/2. That's where the negative 1/2 comes from. Now notice I'm dividing by the square root of 750 minus X, and then I'm dividing again by square root of 750 minus X. So that's the same as multiplying by 1 over this. So it's just going to become 1 over 750 minus X, right? I'll write that out for you so you can see that. So it's going to become minus X minus 1/2. And then it's going to be 1 over the square root of 750 minus X times another 1 over the square root of 750 minus X. See, because I'm dividing here, and that's the same as multiplying by the reciprocal. So this is the same as this piece right here. And that's why when I take two square roots that are the same, I get just 1 over that. All right. Now the negatives are going to cancel. And so this is going to become x over 2 times the 750 minus x. And then I'm supposed to plug in the number 590. And so that's going to become 590 over 2 times 750 minus 590. So let's see, what's 750 minus 590? That's going to be, let's see, 15 minus 9 is going to be 6. And then 6 minus 5 is 160 times 2. So it's 590 over 320. Sorry, I'm making a mess there. Okay, so that simplifies as 59 over 32. And notice now this time the numerator is greater than the denominator, so it's greater than 1, so it's elastic. Okay. Yeah. So that's number 52. So that's how you do those problems. And here's what I was talking about. Number 57. When I said about the maximum revenue. I need to check to see the time here. Hold on. Okay. All right, so we've got 57, and it says for the given demand function. For the given demand function, find the values of X for which total revenue is a maximum. That's the key word right there. Total revenue is a maximum. That means your elasticity equals 1. Okay, so for this type of problem, you need to calculate the elasticity, set it equal to 1, and then solve for X. Okay, so we have 600 plus 7, or X plus 7 squared, 600 over X plus 7 squared. So X equals, I don't know why it says X equals D of X. I don't know why it says that. Just D of X is equal to 600 over X plus 7 squared. And so D prime, okay, this is going to be 600 times X plus 7 to the minus 2 power. So D prime of X is minus 1200 times X plus 7 to the negative 3 power times the derivative of what's inside, but that's just 1. So this is my derivative, and I can write that as negative 1200 over X plus 7 to the power of 3, because that negative just puts it in the denominator. So this is my demand, or the derivative of my demand function. Now that means the elasticity is going to be minus X times this negative 1200 over X plus 7 cubed divided by 600 over X plus 7 squared. And so that is going to be, the negatives are going to cancel. So you're going to have 1200X over X plus 7 cubed multiplied by the reciprocal of this. And so when you simplify that, you're going to get 1200 divided by 600 is 2X, and then X plus 7 cubed in the denominator with x plus 7 squared, and the numerator is going to give you 1x plus 7 in the denominator. This is your elasticity. This is E of x. So we want to maximize revenue. So in order to maximize revenue, you set it equal to 1 and then solve for x. So you can cross multiply. Think of this as 1 over 1. 1 times 2x is equal to 1 times x plus 7. And so we subtract x from both sides, and we get that x equals 2x minus x is x equals 7. So this is what we have to set our price at in order to maximize revenue. Okay. So there will definitely be one like 57 on the test. So make sure you know how to do those type of problems. And 59. This comes from section 4.5 where you do the U substitution. So we're going to integrate 8e to the 4y dy. And so actually, these are actually pretty easy to do. You really don't have to use U substitution, but that is the section that it comes from. You just copy what you see. Whenever you see an E function like this with a multiplied by a constant, you just copy what you see. And then since this is just 4 times y, as opposed to 4 times y squared. If it were squared, it'd be more complicated. But you just divide out by the derivative of your exponent and then add c. So this is going to be 2, or I should say that should be an equal sign, 2e to the 4y. Okay, plus c. So that's not a very interesting problem. Let me do a better one. Aha, 63 is a good one. So we're going to integrate, this is a definite integral from 0 to 1 of 5x to the 4th ex to the 5th dx. Okay, so when you want to integrate, what you'll notice here is you've got a product of 2 separate functions. But what's interesting is this is the derivative of the inside function. And remember, when you do use substitution, it's the reverse of the chain rule. So someone took a derivative of a function and they applied the chain rule because they took the derivative of what's inside. So whenever you see the derivative multiplied by a function with the original function inside there, you know, oh, this is U substitution. You always set U equal to your inside function. See how x to the 5th is inside the E function? And this is on the outside multiplied. So this is your U. So you're going to say U equals x to the 5th. Whatever that inside function is your U. Then you calculate the derivative. And voila, that's right, sitting right there. So what you've got is that du is equal to 5x to the 4th dx, because what I'm going to do here is multiply both sides by dx. And this is what I get. Now, what I see here is 5x to the 4th dx, and that's exactly what I have here. So I can just replace this with du, and then I replace this with u. So I get this integral, and it's e to the u du. Well, remember, these numbers here are on the x-axis, and we're converting everything to u, so we have to convert these numbers as well. So all we do is we take the x and raise it to the 5th power. That's how you change it. Just so happens that 1 to the 5th power is 1. So your u1 is x1 to the 5th power, which is 1 to the 5th power, which is 1. Now, it's not always going to be the same number, but in this particular case, it is. And same with 0. u2 is equal to x2 to the 5th, which is 0 to the 5th, which just happens to be 0. So we get 0 on the bottom. But normally, when you convert them, these numbers are different. Okay, it's just by coincidence this time they're the same. So when we integrate this, we just have e to the u evaluated from 0 to 1, which is just e minus e to the 0, which is e minus 1. All right, let me do another one of these since these are kind of tricky. And I'm still trying to keep track of my time here. Yeah, I'm obviously not going to finish the review today, but like I said, I have another survey of calc class after this one this afternoon, and I'm going to finish up and I'll post all 3 videos covering the entire review. Okay, so number 64. We have the integral from 0 to 1 of x times x squared plus 1 cubed dx. So again, you can see something like the chain rule took place here because we've got this inside function, which is inside the cube now. The last time it was inside the e function. This time our function is inside the cube function. And on the outside is a version of the derivative. The derivative of this inside is 2x, and we don't have 2x, we have 1x, but we're just off by a constant, and we can fix that. So this is an obvious candidate for u substitution. So remember, you always set your u equal to what's inside. So u equals x squared plus 1. And then when you take the derivative, du dx equals 2x. And remember how I said we don't have a 2? So what I'm going to do is I just want plain old x. So I'm going to divide out by 2 on both sides of the equation. And then I want this dx along with my x. I want the dx. So I'm going to multiply both sides by dx. And this is going to go away. This is going to go away. And so what I have then is that du over 2 is x dx. Now I can replace x dx because that's just du over 2. So I have this integral, and x dx gets replaced with du over 2, and x squared plus 1 gets replaced with u. So I have u cubed du over 2. And I can pull that 1/2 out front. So this is 1/2 u cubed du. Now, I still have to do the indices, right? Because these values up here, 0 and 1, are x's, and I want u's because I'm integrating with respect to u. So I want these numbers here to be u's. So I have to convert them. And here's the way I convert them. I take my 1, plug it into this equation. So u1 is x1 squared plus 1, which is 1 squared plus 1. So that's going to be 2. So this 1 as an x becomes a 2 as a u. Okay. Then u2 is x2 squared plus 1, which is going to be 0 squared plus 1 equals 1. So this 0 as an x becomes a 1 as a u. And so this is going to become, now I do the integration. Now that everything is in u, I do the integration, and it's going to be u to the 4th over 4 evaluated from 1 to 2. And don't forget your 1/2 there out front. There's my 1/2. So this is going to be 1/2 times 2 to the 4th over 4 minus 1 to the 4th over 4. So 2 to the 4th over 4, that's 16 divided by 4, that's 4. So we have 1/2 times 4 minus 1/4. So I should have just left it as 16/4. That's what never mind there, 16/4. Because 16/4 minus 1/4 is 15/4. So we have 15/8. And that is our definite integral. Remember, definite integrals have numbers here, and they always equal to a number. An indefinite integral is an antiderivative. It's a function, okay? All righty, so that was number 64. And I feel like we're out of time. Let me check here. I guess we could do one more problem. Let me see here. Well, we're moving on to a new topic, so I'll just save that for my next class and I'll post that video. I'm going to post the videos as soon as I can. So by tonight, I should have them up there unless I run into some complication, but I doubt that. I'm going to mark you down as attending, Kate, so that since I didn't have an assignment, so I'll go ahead and write your name on my attendance sheet here. And there we go. All righty, you're welcome. We'll hope you have a great weekend. See everybody, and like I said, be looking for that email with the review links.